present the research about assessing Ukrainian territory suitability for solar power station placement using satellite data on climate and topography.
Yes. Can you see my screen?
Yes, very well.
So let's start this research. And first of all, I want send second that first of all, it should be mentioned that Ukraine has been at war for a second year. And as a result of Russia's aggressive action, various sectors of Ukraine's economy were affected. In particular, several damages was caused to the energy sector. In the past year, Russia has carried out numerous attacks on energy facilities, as a result of which civilians have sometimes been severely limited in their use of electricity. Sometimes in some settlements, people lived completely without electricity and any communication for several days in a row. In general, during the war, Ukraine lost about 27 gigawatts of generated power. Many energy facilities, such as the Kakhovka electric station, were completely destroyed or are still occupied as the Zaporizhzhia electric station. And as a result, the energy sector of Ukraine needs total reconstruction. At the same time, it is worth mentioned that Europe Green Accords. After all, Ukraine is also a part of Europe, and Ukraine is also joined to the Green Deal. This means that when restoring the energy sector, special attention should be paid to renewable energy facilities, for example, solar power plants. But in order to build efficient solar power plants, we need to choose the right place for their placement. And determining such places is the main goal of this research. In general, the performance of solar power plants is affected by three main external factors. First is climate, then topography, relief, and land use. And we can use remote sensing data to obtain such data about climate, relief, and land use. But in our research, we take into account two main factors like climate and topography. We receive climate data from the Area 5 land searcher, and these data include global horizontal radiation, accumulated temperature, accumulated precipitation like rain and snow, and annual wind, average annual wind speed at a height of 10 meters. And also we use data about relief from Shuttle Radar Topography mission with a special resolution of 90 meters, and these data include elevation, slope, and hill shadow. On this slide, you can see the climate maps that we have created using their raw input data from Area 5 land. And this map were compared with the data from other sources to assess their suitability. For example, we compare the data about solar irradiation with data from solar atlas data, and the correlation coefficient reached to 0.97, and the relative error did not exceed 13% for the data averaged by regions. And on this slide, you can see our created maps about topography. And now let's move to the methodology. To build the map of the suitability of the land of Ukraine for the installation of solar panels, we perform several steps. Our first step is data normalization. That is, the maps that was shown on previous slide were reduced to the difference range from 0 to 1. After this normalization, we assigned weighted coefficient for each parameters. We determine this coefficient using correlation coefficients between the parameters and the performance of solar power plants, drawing information from external sources. On the basis of the received normalization maps and determining parameter weights, we apply the weighted sum methods, which formula is given on the slide. After applying these methods, we obtain a certain land suitability map and normalize it to obtain data in the range from 0 to 1. This way, we get result maps with the value. In these maps, with the value 1 is ideal for land for installing offshore power plants, and 0 mean completely unsuitable land. And on this slide, you can see that map that we have received. This map shows that the best land for installing solar power plants is located in southern Ukraine, and land suitability decreases from south to north. According to the quantitative analysis of suitability, the largest part of Ukraine has a suitability within the range from 0.3 to 0.4. And the total area of territories with a suitability below 0.2 is less than 5,000 kilometers squared, while the area of territory with a suitability above 0.5 is more than 40,000 kilometers squared, indicating that the favorable territory exceeds that unfavorable territory by almost 10 times. And we also assess the location of the most powerful solar power plants that is already available in the territory of Ukraine. From this map, you can see that the most of installed solar farms are located in the optimal zones. These maps show that certain regions of Ukraine with good suitability indicators, such as Odessa, Poltava, Kharkiv, Zaporizhzhia, Dnipropetrovsk, Donetsk, and Lugansk, are underutilized and have high potential for the installation of productive solar power plants in the future. And now let's move to the conclusion. So, as a result of this research, a map of the suitabilities of the land of Ukraine for placement of solar power plants was built on the basis of satellite data. It was established that the main part of Ukraine has a suitability coefficient in the range of 0.3 to 0.4, which corresponds to the average suitability indicators. The best conditions for solar power plants are in south of Ukraine, and the worst are in west region of Ukraine and in the territory of Polisia. The location of existing solar power plants in Ukraine was analyzed, and it was found that some regions with good suitability are underexploited and have a lot of free places for building future productive solar power plants. In the future, we want to involve in the analysis also data on land use and other parameters, such as, for example, economic parameters as distance to the nearest power transmission line, etc. And also, we want to complete our methodology and use fuzzy logic to improve the results of our analysis. So, thank you for your attention.
Thank you very much for the presentations. Are there any questions? To the presenter? No. If not, thank you. Thank you very much. And now I would like to invite the next presenter, and we slightly changed the order of the presentation because the authors of the last presentation have some troubles with communication. So we will try to run the video record of the presentation, which is last in our section. It is Generative Adversarial Network Style Transfer for Sustainable Urban Restoration Planning in Ukraine. The presentation is prepared by Artem Shelestov and Leonid Shumilo. And please
Can you see screen?
Yes.
Okay.
Good afternoon, ladies and gentlemen. My name is Artem Shalastov. I represent the Anhalt University of Applied Sciences, and I want to present to you my project, Generative Adversarial Network Style Transfer for Sustainable Urban Restoration Planning in Ukraine, written jointly with Leonid Shumilo of Department of Geographical Sciences in University of Maryland. Many Ukrainian cities have been damaged or destroyed due to the ongoing Russian-Ukrainian war, which has caused immense infrastructural damages, which are estimated to be at around $138 billion by the Kyiv School of Economics. And right now, post-war restoration efforts are being actively planned, and they are, first of all, focusing on sustainability. For two main reasons. Firstly, to create the best possible living conditions for the citizens of Ukraine, and secondly, to aid with its goals of integrating into the European Union, to which sustainability is one of the biggest factors. And for these tasks, I plan to use urban planning experiences of developed countries, because they already plan their development as with sustainability in mind, which can help the task at hand. Artificial intelligence, computer vision, and image processing have stepped to a whole new level recently and are still rapidly progressing. For example, the recently developed generative adversarial networks have made it possible to augment reality and model data, and they allow to transform images using style transfer, transferring features of one image onto another, which can be used to generate realistic satellite imagery. And these properties of the GIN can be used to apply it to analyze the urban practices of different countries and their suitability for sustainable post-war restoration planning in Ukraine by the means of generating synthetic satellite imagery and analyzing its properties. The data which is ideal for such a network for the input is the street plan of a city, and for the output is a satellite image. The street plans can be created based on the OpenStreetMaps. However, as OpenStreetMaps has many unneeded classes such as labels, place icons, and so on, it has to be modified, which can be done using the service MapTiler, which has also been used to source the satellite imagery, because this means that it can be done in the same resolution and centered on the same point with the same scale, which is vital for a good data set. In the end, 16 images of each type of street plans and satellite images each for each of Italy and Poland have been sourced. Each of the images has resolution of 2048 by 2048 pixels, and they have been split into training windows of size of 256 by 256 pixels, with a step of 215 pixels, resulting in 5,184 total windows which have been used for model training. The windows are also intersecting with each other, which has a positive impact on the overall result of the model's work. For this work, the main method used was the general adversarial network, which is a combination of two neural networks of a generator and a discriminator, which are always in a state of competitive training. The generator is a model which is producing data based on set input, while the discriminator is trying to classify the synthetic data as either realistic or fake. And these two models are in a state of adversity with each other, giving the name to the network. They are constantly improving each other, which leads to extremely impressive results. There is a particular type of a general adversarial network which is used in this study, which is a pixel-to-pixel or simply pix-to-pix GAN, which allows for image-to-image translation using some set of conditions. And what it does is basically transfer the features of the input image into the space of the features of the output image. And it is great for feature extraction and multimodal image generation. And it is possible to use such a GANs for style transfer to learn features of urban planning styles and translating them to destroyed cities by the means of creating synthetic satellite images. The model used in this study is a pixel-to-pixel GAN model, which uses a UNet architecture. It is comprised of 7 encoder and 7 decoder blocks, which have a max pooling function and an uptranspose function, respectively. For the convolutional blocks or the encoder blocks, leaky ReLU activation function has been used, the function of which you can see on the bottom left of the slide. And the sigmoid activation function has been used for the output layer, which the formula for which you can see below the formula for leaky ReLU. Because this model has a UNet architecture, skip connections have been added between layers, which is indicated by the dotted lines on the scheme. To train the model, the ADAM optimization algorithm with values of beta at 0.5 and a learning rate of 0.01 has been used. And the discriminator loss function is the classic binary cross entropy, which is extremely popular for such tasks. And the combined loss function is a linear combination of the discriminator loss and a mean square error function. The formula for which each of the discriminator and combined loss functions can be found in their respective spaces on the slide. To analyze each of the urban planning styles' efficiency, green space coverage has been chosen as an indicator because green zones are often used to analyze urban planning as they have an extremely significant impact on the livability of a space. And efficient planning has been made tied to such issues as urban islands, reduced air quality, and others. To classification into a green space and green space class to analyze their coverage has been done by the means of feature crossing of the spectral channels of the satellite images generated by the model. As a result of the study, two models have been created. The first one generates in an Italian style. A case study of Mariupol has been used to illustrate the working of the model. And you can see the generated image itself, a composite image of resolution 2048 by 2048 pixels, comprised of images, smaller images of 256 by 256 pixels on the left, and its respective green zone mask on the right. And it has been found to have a 5.32% green space coverage, and as you can see, the green spaces tend to be concentrated in similar places with each other, and there is a rather peculiar feature, which is a green space along one of the main roads pictured in the image. The other model generated images of Mariupol in Polish style, and its respective green zone mask can also be seen on the right. And it can be noted that both the resulting image and the green space mask are wildly different from those produced by the Italian model. Firstly, because it has a significantly higher coverage of 7.18%. And green spaces in this picture tend to be distributed more between the buildings, for example, which you can see in the center of the picture. Here we can have a comparison of the two models' green space masks. And it can be seen in the two main areas of interest, a lot of differences. Firstly, in the one in the bottom, we can see how sparser the green zones in the Italian model are. And on the one on the top, we can see that the green space along the main road is largely not present on the Polish model. However, there is more green space in between the buildings in the center of the picture, which I mentioned before. And just looking at the general amount of green spaces, the significant difference in amount can be seen with the naked eye. This method is applicable for post-war restoration because it can be used to compare different urban planning styles using a number of factors, for example, green space coverage, and as well as many others. Because similar models can be trained to analyze urban planning styles of any countries, and the models can be then applied to any area in any country, we can note that this method is extremely versatile and can allow to compare a huge number of different urban planning styles, which can be then used to estimate which one is best suited for the restoration of any specific given area in the country which is being discussed. So in this case, Ukraine. In conclusion, generative adversarial networks have been proven efficient for the urban restoration planning in Ukraine by being useful to highlighting the significant impact the urban planning styles have on both green space total area and their location, so their distribution, which is a major factor on the livability of a space. Also, it improved the general understanding of their influence on environment design, as noted in the comparison. And valuable insights have been gained, firstly, by creating a method which allows to account for green space proportions while planning urban restoration and using other countries' experience. and an analysis and comparison is made possible of any country's planning styles in any location. Thank you very much.
Thank you very much for the presentation. And are there any questions to the authors? They are here and already.
Yeah, I have a couple if I can
Yes,
to
please.
ask. Thank you, Artem, for your great presentations. It's very important, especially at the current moment. You described your task in terms of models, GAN networks, and so on. But I would like to ask you maybe again about data which have you used in your tasks and your research. As I understand, you used mainly optical data. Maybe you have some thought about radar data which can be embedded in your task and your research. Thank you.
Thank you very much for your question. In the project, I have used two main types of data. Firstly, it was modified OpenStreetMaps data, which has only been left with the classes which represent land cover or land use, which is buildings, industry, road types, and so on, without any text, icons, and others. And the other part of the data has been high-resolution satellite imagery, which have been both sourced from the same service, which allows to export these images in the same scale and the same center point, which makes them suitable for a data set of this kind.
Yeah, thank you. More questions, please?
Maybe for common understanding, if I understand, you used GAB networks. It's known that that is hard solution from processing point of view. Is it enough some local resources, or you use some cloud services for processing your data?
For the training, I have used only my personal equipment, only my personal hardware, and it has been suitable for the training of the models. However, it takes an extremely long time, and if there is any mistake, it is extremely costly, especially in the data set.
Yeah,
Thank you. More questions, please, if any. So thank you very much for